Chapter 1: Matrices and Transformations. So far, we know 4 types of transformations: reflections, rotations, translations, and enlargements. A reflection is a transformation that flips a shape over to create a mirror image. In a reflection, the object and its image are the same size and shape, but are laterally inverted with respect to each other. The dotted line of reflection is called the mirror line. It is sometimes called the axis of reflection. Under a reflection, 2 corresponding points are equidistant from the mirror line. A reflection is described by the equation of the mirror line. A rotation is a transformation that turns a shape through a certain angle about a fixed point. In this example, the figure was rotated anti-clockwise. In a rotation, the object and its image are the same size and shape. The point about which a shape is turned is called the center of rotation. A rotation is fully described by the center and angle of rotation. A translation is a transformation that moves or slides a shape through a given distance in a given direction. Under a translation, all points on the image move through the same distance and in the same direction. The size, shape, and orientation of the object is not changed under a translation. Therefore, points on the object can be joined to corresponding points on the image by a set of straight lines which are equal and parallel. A translation is fully described by a vector because it has both magnitude and direction. In this example, each point was moved 9 places to the right and 4 places upwards, so the translation vector is 9, 4. An enlargement is a transformation that increases or decreases the size of a shape. The sizes of the sides of the shape increase proportionately. In this example, the image is twice the size of the object. Each side on the image is twice the size of the corresponding side on the object. The angles, however, do not change. We say the object has been enlarged by a scale factor of 2. If you join the corresponding points on the image and object, they intersect at a point. This is the center of enlargement. An enlargement is fully described by the center of enlargement and the scale factor. In this chapter, we look at 2 more transformations: shears and stretches. We start with shears. Now, consider this pile of books on a table forming a 3D shape of a cuboid. If the pile was pushed carefully in this direction, the shape appears more of a parallelogram. Notice that the lowest book in contact with the table does not move, and that is because the table did not move. The top of the table is said to be invariant, and the book in contact with it is invariant as well. Notice that the direction of displacement is parallel to the invariant table surface. This kind of a transformation is called a shear, a transformation that keeps one line invariant and all the other points move parallel to the invariant line. The topmost book moved the longest distance, or it was most displaced, and that the bottom one was displaced the least distance, that is 0. The topmost book is farthest from the invariant line and thus moved the farthest than the rest. In a shear, the distance moved by each point is proportional to its distance from the invariant line. The constant of proportionality in this relationship is called the shear factor. Let's call it S. S is equal to distance moved by a point over the perpendicular distance of the point from the invariant line. We can make that simpler by saying S is equal to displacement over the perpendicular distance. Given the shear factor and the perpendicular distance, you can find the displacement by simple cross multiplication. Displacement is equal to the shear factor times the perpendicular distance. Always remember, it's perpendicular distance from the invariant line, and displacement is always parallel to the invariant line. When the S is positive, displacement is to the right or upwards. And when it's negative, displacement is to the left or downwards, depending on the invariant line. For example, we have triangle ABC and we want to get its image under a shear factor 3 with y is equal to 1, the invariant line. Two things to remember. 1. Points B and C lie on the invariant line, and so they don't change. Only point A will change. Number 2. The shear factor is a positive, so displacement is to the right. Remember, it has to be parallel to the invariant line. So how much will A be displaced? Perpendicular distance from the invariant line is 2 units. S is 3, and so displacement is equal to 2 times 3, which is 6. So it has to be displaced 6 units to the right. 1, 2, 3, 4, 5, 6. This is our new A prime. B and C don't change, and so we have triangle A prime BC as the image. If the shear factor was, say, -4, then displacement will be equal to 2 times -4, which is equal to -8. And so that is a displacement of 8 units leftwards. So 1, 2, 3, 4, 5, 6, 7, 8. So that would be the new figure. What if only one point lie on the invariant line? We have triangle PQR undergoing a shear with a shear factor 3, y is equal to 1 invariant. Point Q lie on the invariant line, so it does not change. P and R will be displaced, but by how much? Let's start with P. Perpendicular distance from the invariant line is 2 units. S is equal to 3. Displacement is equal to 2 times 3, which is 6 units to the right. 1, 2, 3, 4, 5, 6. This is P prime. Point R. Perpendicular distance from the invariant line is 1 unit. S is 3, so displacement will be equal to 1 times 3, that is 3 units to the right. So 1, 2, 3. Joining the 3 points, this is the figure we obtain. If the shear factor was a negative, we will displace the points leftwards. What if no point lie on the invariant line? All of the points will be displaced. We have triangle MNO to undergo a shear factor -3 with the line y is equal to 0 invariant. So this time the x-axis is the invariant line. We start with point M. Perpendicular distance from the invariant line is 3 units. S is -3, so displacement will be equal to -3 times 3, which is -9. That is 9 units to the left. M prime is here. Point N. Perpendicular distance from the invariant line is 1 unit. S is the same -3, and so displacement is -3 times 1, which is -3. So we move 3 units leftwards. So N prime is here. Lastly, point O. Perpendicular distance is 2 units. Shear factor is -3. Displacement is -3 times 2, which is -6. So we move 6 units leftwards. And O prime is here. If we join all the 3 points, this is our new triangle as a product of the shear process. Shear transformations parallel to the y-axis work in a similar manner. Consider triangle ABC to undergo a shear by shear factor -4 with the line x is equal to 3 being invariant. Point A. Perpendicular distance from the invariant line is 2 units. S is -4 and displacement is -4 times 2, which is -8. So we move 8 units downwards. A prime is here. Point B. Perpendicular distance from the invariant line is 1 unit. S is -4 and displacement is -4 times 1, giving us -4. So we move 4 units downwards and B prime is here. Finally, point C. Perpendicular distance is 3 units. S is -4. Displacement is equal to -4 times 3, which is -12. So we move 12 units downwards. C prime is here. If we join all the 3 points, the transformed figure is A prime, B prime, C prime. Now, so far, we know that a negative shear factor displaces points leftwards or downwards. But something else also displaces the points leftwards and downwards. If you look in all the examples, I was careful enough to keep all the figures either above the invariant line. For example, this triangle MNO was above the invariant line, the x-axis, or in front of the invariant line. For example, this triangle ABC was in front of the invariant line, x is equal to 3. Suppose now the figures were below or behind the invariant lines. What would happen if this triangle MNO was below the x-axis, which is the invariant line? Or this triangle ABC was behind the line x is equal to 3? In these cases, we take the perpendicular distance to be negative. We then proceed to multiply with the shear factor and get the displacement. For example, draw the image of triangle PQR under a shear factor 2 with x-axis invariant. Let's start with P. Perpendicular distance will be -4. S will be 2. Displacement is -4 times 2, giving us -8. So we move 8 units leftwards. This is P prime. Point Q. Perpendicular distance from the invariant line is -1. S is 2. Displacement is -1 times 2, giving us -2. So we move 2 units leftwards. Point R. Perpendicular distance is -1 units. S is 2 and displacement will be -1 times 2, giving us -2. So we move 2 units leftwards. This is the transformed figure. Another example. Map the image of triangle XYZ under a shear factor 3 with x is equal to 8 invariant. We start with point X. Perpendicular distance from the invariant line is -1. S is 3. Displacement is -1 times 3, giving us -3. So we move 3 units downwards. Point Y. Perpendicular distance from the invariant line is -2 units. S is 3. Displacement is -6. That is -2 times 3. So we move 6 units downwards. Point Z. Perpendicular distance is -3 units. S is 3. So displacement is -3 times 3, giving us -9. So we move 9 units downwards. This is the image. Now, this understanding is important when dealing with cases where the invariant line passes through the figure itself. Consider this example. Rectangle ABCD is to be mapped under a shear factor 2 with the line x is equal to 3 invariant. Notice that points A and D are behind the invariant line, while B and C are in front of the invariant line. Attempt on your own to map the image by following what we've done. Expect an image with one side displaced upwards and the other side downwards. Good luck. Next transformation, stretches. Now consider a spring fixed onto a red surface. If the spring is pulled, it stretches out. When pushed, it compresses back. However, in either cases, the red surface does not move. It is an invariant line. Notice that all the other points on the spring move perpendicular to the invariant line. This is a stretch, a transformation that keeps one line invariant and all the other points move perpendicular to the invariant line. So in a stretch, displacement is perpendicular to the invariant line. Points on the invariant line are also invariant. The stretch factor m is given by image distance from the invariant line over the object distance from the invariant line. So given m and the figure, you can calculate the image distance. That is, image distance is equal to m times the object distance. Note that all distances are measured from the invariant line. For example, map triangle PQR under a stretch factor 2 and y-axis invariant. Let's start with P. Object distance from the invariant line is 2 units. M is equal to 2, and therefore the image distance will be 2 times 2, which is 4. So the point moves 4 units from the invariant line to the right. Point Q. Object distance is 4 units from the invariant line. M is 2. Image distance is given by 4 times 2, which is 8. The point will therefore move 8 units to the right from the invariant line. Finally, point R. Object distance from the invariant line is 3 units. M is 2. Image distance will be given by 3 times 2, which is 6. And so the point moves 6 units to the right from the invariant line. And there is our image. What if we transform the triangle by stretch factor -2 with the x-axis invariant? Negative means the stretch is downwards or leftwards. In this case, it will be downwards. Point P. Distance from the invariant line is 1 unit. M is -2, so image distance will be -2 times 1, giving us -2. So we move 2 units downwards. This is P prime. Point Q. Distance from the invariant line is 1 unit. M is -2. Image distance is -2 times 1, giving us -2. So again 2 units downwards. Finally, point R. Distance from the invariant line is 3 units. M is -2. Image distance -2 times 3 is -6. So we move 6 units downwards. This is R prime. So P prime, Q prime, R prime is the image of triangle PQR under a stretch factor -2 with the x-axis invariant. Now, just like in shears, when the object is below or behind the invariant line, the object distance is negative. An object can also undergo a two-way stretch, which is a combination of 2 successive stretches, one after the other. For instance, consider the square ABCD. Let it undergo a stretch factor 2 with x-axis invariant, and then a stretch factor 3 with y-axis invariant. Let us do the first stretch, x-axis invariant. In this case, the image is below the invariant line, and so the object distances are negative. Also, points A and D lie on the invariant line, and so they won't change. Point B, distance from the invariant line is -3. M is 2, so image distance is -3 times 2, which is -6. So we move 6 units downwards. Point C, distance from the invariant line is -3. M is 2, image distance will be -3 times 2, which is -6. So again we move 6 units downwards. So we have our B prime, C prime. Now, this new figure is to undergo the second stretch with the y-axis invariant. In this case, the figure is in front of the invariant line, and so the object distances will be positive. Also, points C and D will be invariant. A and B will change. Point A, object distance is 3 units. M is 3 in this case. Image distance, 3 times 3 is 9. So we move 9 units to the right. Point B, object distance is 3 units. M is 3. Image distance is 3 times 3, which is 9. So again we move 9 units to the right. And this is the final image of the 2 successive stretches. Always remember that shears move points parallel to the invariant line, while stretches move points perpendicular to the invariant line. Next, transformation matrices. Now, when it is not mandatory, it is easier to transform figures through calculations rather than constructions. Matrices provide an easier way of working out the coordinates of points on the image after a transformation in certain special cases. Let's see that. Consider a unit square OIJK on the Cartesian plane. If you take the points I and J and write their coordinates in vector form, I is equal to 1, 0 and J is equal to 0, 1. If you combine the two, you form a matrix 1, 0, 0, 1. This is what we call an identity matrix. Using these 2 points, I and J, we can always form a 2 by 2 matrix for a given transformation. Take an example, a shear transformation. Suppose we want a shear matrix for scale factor 2 with y-axis invariant. We go to the unit square and consider points I and J and subject them through that transformation. In this case, point J will be invariant because it lies on the invariant line, so its coordinates remain J prime 0, 1. How about I? In shear, a point moves parallel to the invariant line, so displacement is equal to perpendicular distance from the invariant line times S, the shear factor. In this case, we shall have 1 times 2, which is 2. And so point I will move 2 units upwards. The new coordinates will be I prime 1, 2. If you write I prime and J prime as column vectors, I prime will be equal to 1, 2 and J prime is 0, 1. As a matrix, you shall have 1, 0, 2, 1. This is the shear matrix for the scale factor of 2 with y-axis invariant. Given any coordinates, you simply multiply with this matrix to obtain the coordinates of the image. In this matrix, 2 is the scale factor. If the scale factor was 3, the shear matrix with y-axis invariant would be 1, 0, 3, 1. So in general, the bottom 0 of the identity matrix is replaced by the scale factor when the y-axis is invariant. And so the shear matrix with y-axis invariant is 1, 0, S1, where S is the shear factor. If you repeat the process with x-axis now invariant, you will find that point I will be invariant and that J will have new coordinates 2, 1. So the shear matrix when x-axis is invariant will be 1s, 0, 1, where s is the shear factor. For example, triangle ABC with coordinates A, 1, 1, B, 3, 1, and C, 2, 4 undergoes a shear transformation with x-axis invariant and shear factor -3. Write the coordinates of the image. If you don't have the transformation matrix for this shear, you simply draw a unit square and subject I and J to the transformation. It will give you the matrix. In this case, the matrix will be 1s, 0, 1. S in our case is -3, and so the matrix is 1 minus 3, 0, 1. We multiply each point on the triangle with this matrix. Point A, 1, 1, so we have 1 minus 3, 0, 1 times 1, 1. 1 times 1 plus minus 3 times 1 is minus 2. 0 times 1 plus 1 times 1 is 1. So A prime has coordinates minus 2, 1. Point B, 1 minus 3, 0, 1 times 3, 1 will give us 1 times 3 plus minus 3 times 1 is 0. 0 times 3 plus 1 times 1 is 1, and therefore B has coordinates 0, 1. Do the same with C. 1 times 2 plus minus 3 times 4 is minus 10. 0 times 2 plus 1 times 4 is 4. Therefore C has coordinates minus 10, 4. In fact, to save time, the vertices of the triangle can be put in 1, 2 by 3 matrix. And so we'd have the shear matrix 1 minus 3, 0, 1 times 1, 3, 2, 1, 1, 4. And then you proceed and multiply. We start with the x coordinates. 1 times 1 plus minus 3 times 1 is minus 2. 1 times 3 plus minus 3 times 1 is 0. 1 times 2 plus minus 3 times 4 is minus 10. Then the y coordinates. 0 times 1 plus 1 times 1 is 1. 0 times 3 plus 1 times 1 is 1. And then 0 times 2 plus 1 times 4 is 4. And so we have the matching coordinates. Notice that the y coordinates did not change because the displacement was parallel to the x-axis and there was no vertical displacement. Attempt the same transformation, but now with y-axis invariant. Notice that the shear matrices only work when the invariant lines is either the x-axis or the y-axis and not any other line. Any other line, the solution will have to be construction. In the same way, we can easily obtain a stretch matrix for x and y axis being invariant. Consider a stretch factor of 3 with x-axis invariant. What will be the stretch matrix? We go to the unit square and consider points I and J under the same stretch. In stretches, points move perpendicular to the invariant line and distances are taken from the same invariant line. Because x-axis is invariant, point I is invariant, and so it remains I prime 1, 0. What of point J? J prime will be image distance is equal to m times object distance. That is 3 times 1 giving us 3. So it will be 3 units from the invariant line. Its coordinates will be J prime 0, 3. As vectors, I prime is equal to 1, 0 and J prime is equal to 0, 3. As a matrix, that will be 1, 0, 0, 3. In general, the stretch matrix with x-axis invariant is given as 1, 0, 0, m, where m is the scale factor. If you repeat the same for y-axis invariant, the matrix will be m0, 0, 1. For example, triangle PQR with coordinates P12, Q35, and R30 undergoes a stretch by factor -2 with y-axis invariant. Calculate the coordinates of its image. So the stretch matrix for y-axis invariant, in this case factor -2, will be -2, 0, 1. We multiply by the coordinates of the triangle PQR and we'll find that P prime will be -2, 2, Q prime -6, 5, and R prime -6, 0. Next, rotation matrices. Again, unless required to, you can avoid doing construction of figures when the center of rotation is at the origin 0, 0. We use matrices. To find the matrix, you get the same unit square and consider points I and J. Rotate the points through the required angle and get the new coordinates. Using them, form a matrix and you shall get the rotation matrix. For example, point P with coordinates 5, 7 is rotated through -90 degrees. Write the coordinates of its image. This is the unit square. We need to find the rotation matrix for -90 degrees. We rotate I and J, and this you can do with your eyes. -90 degrees means clockwise rotation. If I is rotated -90, it will be here, I prime 0, -1. If J is rotated -90, it will be here, J prime 1, 0. As vectors, I prime is equal to 0, -1, and J prime is equal to 1, 0. As a matrix, that is 0, 1, -1, 0. This is the rotation matrix for -90 degrees about the origin. So we multiply the coordinates of point P with this one to get P prime. 0, 1, -1, 0 times 5, 7. 0 times 5 plus 1 times 7 is 7. Minus 1 times 5 plus 0 times 7 is -5. And so P prime has coordinates 7, -5. Attempt the same with a rotation of +90 and 180 degrees. Once again, notice that the matrices of rotation only work when the center of rotation is the origin, 0, 0. Reflection can also be done using matrices. We use the same unit square and reflect the points I and J. For example, consider point M with coordinates -9, 6 to be reflected on the line Y is equal to -x. We find M prime. First, we find the reflection matrix for Y is equal to -x. We get our unit square. The line Y is equal to -x is this one. Now reflect I and J on that line. I prime will be 0, -1, and J prime will be -1, 0. As vectors, I prime is equal to 0, -1, and J prime is equal to -1, 0. As a matrix, that will be 0, -1, -1, 0. This is the reflection matrix for Y is equal to -x. We multiply M with that. 0 times -9 plus -1 times 6 is equal to -6. -1 times -9 plus 0 times 6 is 9. So M prime has coordinates -6, 9. And so you see, by using the unit square and transforming points I and J, we can create the matrices of transformation for special cases and calculate the coordinates of the images. Finally, the enlargement matrix. Now, the 2 by 2 enlargement matrix has the general form K0, 0K, where K is the scale factor with center of enlargement 0, 0. Any other center of enlargement cannot work with matrices. Recalling similarities and enlargements, K is the linear scale factor, and therefore K squared will be the area scale factor. For example, triangle ABC with coordinates A 35, B 11, and C 31, and area 4 square units undergoes an enlargement with scale factor 4 with center of enlargement at 0, 0. Calculate the coordinates and the area of the image. So the enlargement matrix will be 4, 0, 0, 4. And then we write the coordinates of the 3 vertices as 1, 2 by 3 matrix. We then multiply by the enlargement matrix. If we do that, A prime will have coordinates 12, 20, B prime 4, 4, and C prime 12, 4. Area scale factor will be equal to 4 squared, giving us 16. And so the area of the image will be 16 times 4, giving us 64 square units. Next, successive transformations. Now, an object can undergo several transformations one after the other. This is done such that the image of the preceding transformation becomes the object of the next transformation. When an object A undergoes a transformation N followed by another transformation M, this is written as MNA. The first transformation is the one next to the object. In this case, it's N. So the object first undergoes transformation N, and then the results undergoes transformation M. That order is very important. In fact, we can have a single matrix for both M and N by first multiplying them together. The resulting matrix R is then multiplied with the object. So given MNA, if Mn is equal to R, then MNA is equal to RA. For example, a point P with coordinates 4, 5 undergoes a reflection on the line y is equal to x, followed by a rotation of negative 90 degrees about the origin. Find the coordinates of the final image. First is reflection followed by rotation. So we can represent that as TFP, where T is rotation and F is reflection. First, we work out TF. The reflection matrix on y is equal to x is 0, 1, 1, 0. The rotation matrix for negative 90 degrees about the origin is 0, 1, negative 1, 0. So T times F will be equal to 1, 0, 0, negative 1. Then we multiply this product with P. So 1, 0, 0 minus 1 times 4, 5 will give us 4 minus 5. And so the final point will have the coordinates P for negative 5. Next, inverse of a transformation. The inverse of a transformation reverses the transformation. This means that the final image is mapped back onto the original object. For example, if a figure is rotated positive 90 degrees, then the inverse is a rotation of negative 90 degrees about the same center of rotation. A matrix that maps an image back onto its object is called the inverse of the matrix of transformation. If M is a matrix representing a transformation, then its inverse is given as M negative 1. Therefore, Given a transformation MA is equal to A prime, then M negative 1 times A prime is equal to A. Knowing the matrix of a given transformation, it is possible to know its inverse. For example, 1, 3, 0, 1 is a shear matrix of scale factor 3 and x-axis invariant. 3 represents the shear factor. The inverse of this matrix will be 1, negative 3, 0, 1. We change the sign of the element in the matrix representing the shear factor. 1, 0, negative 2, 1 is a shear matrix with scale factor negative 2, y-axis invariant. The inverse of this matrix will therefore be 1, 0, 2, 1. How about stretch matrices? A stretch matrix with scale factor m, y-axis invariant is given by m0, 0, 1, and with x-axis invariant is given by 1, 0, 0, m. M stretches the figure in a certain direction and thus changing its size. To reverse the image back to the object, we have to reverse the two things, size and direction. To change the direction, we reverse the sign. To change the size, we replace m with 1 over m. And so we have the inverse of m001 is equal to negative 1 over m0, 0, 1. And the inverse of 100m is equal to 10, 0, negative 1 over m. So 3001 is a stretch matrix of scale factor 3 with y-axis invariant. Its inverse will be minus 1 over 3, 0, 0, 1. How about enlargement? The enlargement matrix about the origin is given by K0, 0K. Enlargement changes the size. The image is K times the object. It means the object is 1 over K, the size of the image. And so the inverse of K0, 0K will be 1 over K0, 0, 1 over K. We do not change the sign. It means that the inverse of negative 2, 0, 0, negative 2 will be equal to negative a half 0, 0, negative a half. What about reflection? To map the image back onto the object, you simply reflect the image onto the same mirror line. So the inverse of a reflection matrix is the same matrix. Determinant of a matrix and area. Now, under some transformations, the size and shape of objects do not change, while in other transformations, they do. When a matrix represents a transformation, the ratio of the area of the image to the area of the object is equal to the determinant of the matrix of transformation. Therefore, image area over the object area is equal to the determinant. For example, a triangle with vertices A, 0, 0, B, 4, 0, and C, 4, 3 is transformed under the matrix 1, negative 2, negative 1, 4. Find the coordinates of the image and the areas of the two figures. If we multiply the coordinates by the matrix of transformation, we shall get A prime is 0, 0, B prime will be 4, negative 4, and C prime will be negative 2, 8. Area of the object. The object is a right-angled triangle with AB and BC being perpendicular. AC is the hypotenuse. If you look at the coordinates, AB is equal to 4 units along the x-axis, BC is 3 units parallel to the y-axis. Therefore, area is equal to a half times 4 times 3, giving us 6 square units. Area of the image over the area of the object is equal to the determinant. we already have the area of the object, 6 square units. The determinant, we multiply 1 times 4 minus 1 times 2. That is 4 minus 2, giving us 2. And so the image area over the object area is equal to 2. Image area over 6 should be equal to 2. Cross multiplication, and the image area is 12 square units. So in summary, to transform a point xy by a matrix A, B, C, D, we multiply the two matrices A, B, C, D times xy. To find a transformation matrix, we use the unit square. We take I and j and transform them, and we will get the matrix. There are 6 types of transformations: shear, stretch, translations, rotations, reflections, and enlargements. Shears move points parallel to the invariant line. The general shear matrix with x-axis invariant is 1s, 0, 1, and with y-axis invariant it's 1, 0, s1, where s is the shear factor. Stretches move points perpendicular to the invariant line. The general stretch matrix with x-axis invariant is 1, 0, 0, m, and with y-axis invariant it's m0, 0, 1, where m is the scale factor. Translations are represented by a vector, or you can see it as a 2 by 1 matrix. To translate a point xy with vector AB, you simply add the 2, xy plus AB. The general enlargement matrix is K0, 0K, where K is the scale factor or the linear scale factor and K squared the area scale factor. Notice that K squared is the determinant of the matrix. Rotation about the origin and reflection matrices are determined using the unit square. The inverse of a matrix will map the image back onto the object. The determinant of a transformation matrix gives the scale factor for area. A singular matrix, that is one with a determinant of 0, will map all points to a straight line.
I love that math generally has initially clear and precise answers, that you know when you know it and you know when you don't know it. As you get farther on in it, the answers are not so clearly in the back of the book, but initially math has answers, clear answers. Sometimes they're hard to find, but that clarity. The second thing I love about math is it's a puzzle-solving kind of, if I can figure it out, and the joy of figuring it out, the kind of sense of accomplishment, the sense of excitement when you get it, the challenge of trying to get it. It's that puzzle-solving kind of thing that I really, really like.